Next problem. We're going to meet here one of the biggest problems in all of machine learning and even in probability and statistics. This is a problem that occurs all over the map. In fact, it already occurred in decision trees, but it wasn't as bad there, so we didn't focus on it. But we're going to deal with this problem apropos of rule induction because there it's a huge problem, but this problem will occur again. In fact, there's whole subfields of machine learning dedicated to dealing with this problem. And in areas like, for example, like speech recognition, the problem that we're going to talk about is a good chunk of the whole speech recognition is about dealing with that problem, or in natural language processing, for example. So what is that problem and what can we do about it? It's the problem of estimating probabilities from a small sample. If my rule has a probability of 80% based on 1,000 examples, I'm confident. If it has a probability of 80% based on 10 examples, I am not so confident. Okay. And so as I induce the rule, as it grows longer and longer and covers fewer and fewer examples, my decisions become more and more random. Until at some point, the antecedents that I'm adding are just garbage. Okay? So last time we saw, some ways of fighting this, right? What's one way that we use for decision trees that we could also use here? Something from Stats 101.
T-square.
Yeah, I can do a significance test, right? This is one option. And, it works fairly well. But there's actually a much simpler option that typically works just as well or even better. Shockingly simple. So let's see what that option is. So let's see, this is my estimate of the accuracy, right? P is the probability of, the example being true. M1 is the number of true examples covered by the rule. M0 is the number of false examples. And P is just M1 over M0 plus M1, right? Clearly this becomes very unreliable when M1 and M0 are small, okay? So how might we fix this? Any ideas? You're allowed to read the slide. Just say it in your own words. Here's a really, really simple idea. Remember when I talked, when we mentioned before, Monsieur de Laplace and his principle of indifference? His principle of indifference was inspired by the following deep philosophical question. See, philosophy is relevant. We're going to prove that right here, right? It's relevant to computer science. How do I know that the sun will rise tomorrow? You didn't know coming in here today, at 6:30 p.m. on a Thursday that we'd be talking about such esoteric things, right? But bear with me for a second, right? How do I know? I don't know, right? It's always risen so far, right? But maybe tomorrow, the sun will go nova and, or it will die, right? How do I know? So Laplace's answer to this question, which you could say is a shallow answer, or it's actually a deep answer, is the following. In the beginning, right, I haven't seen the sun rise on any day yet. I don't know, right? So I just say that the sun has a 50-50 chance of rising, right? That's his principle of indifference, okay? So before I've seen any example, it's 50-50. But then, the dawn of the first day, right? That glorious moment, the sun rises for the first time. Should that change your probability of the sun rising? Well, yeah, sure, right? Otherwise you're ignoring the data. But should you suddenly believe that because the sun rose one day, it's going to rise every day? That seems a little too much, right? So the question is what can you do that's between 50-50 and, 100-0? What might you do? And, by the way, let's split this forward, right? Once the sun has risen for 2 days, right, I should get even more confident that the sun is going to rise, right? And once the sun has risen for, 5 billion years, right, at that point I should be pretty darn confident that the sun is going to keep on rising, but still not 100% confident because one day the sun will not rise. So what might we do? Right, say day 2. So day 0, or, before the sun rises for the first time, your estimate is 50-50. Or, 1 and 2, right? After the sun has risen one day, what might your new estimate be?
1.5 by 2.
Yeah, something like that, right? So, how about the following? I add 1, right, before I had 1 and 1, right? And now what I do is I'm just going to pretend that I started out seeing 1 of each. So now what happens is that I've seen 2 of the sun rising and 1 of the sun not rising. Right? This is really the Laplace idea, right? So my new estimate is going to be 2/3, right? It's actually gone up substantially, but definitely not to 100%. Okay? Did everybody follow this idea? So we get the following thing that's often called the Laplace estimate. which can take a lot of forms, but here's one, the simplest one. I'm just going to add half to the numerator and 1 to the denominator. I could also add 1 and 2, or 2 and 4. We'll look at that in a little bit. But so this is my Laplace estimate. So first of all, what is my Laplace estimate if I haven't seen any data? 1/2. Right, very good. What is my Laplace estimate if I've seen infinite data? Let's suppose that I have seen infinite examples where the sun rises and no examples where the sun does not rise. Now what is my probability that the sun rises?
1.
It's 1, as it should be, right? So what happens with this very simple thing is that as I see more data, it asymptotes to perfect confidence, or to what the probability really should be, right? Let's say that the sun, on some weird planet rises, 2/3 of the time, right? Then after a while, what I have is 2/3, plus or minus epsilon. This is exactly what we want, okay? So with this very, very simple change, right, from this to this, all I did was add 0.5 to the numerator and 1 to the denominator, and I actually have something that can handle small amounts of data. This one little change that will take you about 10 seconds to make in your code is the difference between a rule induction system that fails miserably and is a great success. This is the greatest bang for the buck that you've probably ever seen in any area of computer science, right? Type these 10 characters and, quintuple your results. Not bad, okay? But now you could ask yourselves, well, why should that be 0.5 and 1, right? Maybe I have some prior reason to believe that, the sun rises some percentage of the time. Let's say I'm building a rule for spam, and 90% of my email is spam, right? Why should I start my rule with the assumption that it's going to be 50-50? That seems silly, right? We know it's not going to be 50-50, right? So what might I do instead? Right? We're looking at a generalization of the Laplace estimate, right? What could I have here instead of 0.5 and 1? There's,
On the top, put the percentage of the time you expect it to be true, and on the bottom, 1.
Exactly, right? In fact, the short answer to the question, what could I have here, is anything. We could put any numbers that we want here, as long as the number of top is not larger than the number on the bottom. Okay? But typically what you will do is you will have the ratio of these two numbers be your prior estimate of the probability, right? If I priori I think it's going to be true with probability 0.9, then that's what I do. I put 0.9 and 1. Okay? Step 1. Step 2. But why put 0.9 and 1 and not, 9 and 10? What is the difference between those two? In fact, what is the difference between, putting down 0.51 or putting 5100? Or for that matter, 5,000, 10,000? What is the difference between these cases, right? Your prior estimate in all of them is 0.5. So what difference does it make?
One skews it more towards whatever, if you have 5,000 over 10,000, you're going to skew it far more towards, your earlier estimate, as opposed to the data you have.
Precisely. The larger I make those numbers, the stronger my prior belief. If I make those numbers small, my prior belief is weak. It will be overridden by the data very quickly. If I believe in those numbers very strongly because I have very concrete, positive information that they're true, then I need a lot of data to override them, and then I make it, and then I make them large numbers. Okay? Again, a very simple thing to play with that has a very large effect on the results. In fact, every good learning algorithm has one good overfitting control parameter, and this is such a parameter. Just varying this parameter goes all the way from overfitting widely, right, if I make it, 0, to basically ignoring the data, right? If I make those numbers much larger than the size of the data has no effect. And in fact, something that is often used in practice in areas like, for example, speech and language is to make these numbers very, very small. They can be smaller than 1, too. Those numbers are just there as a placeholder until I see any data. As soon as I see some data, I start to believe the data. But what I don't want to have is 0 over 0, right? Because that would be a lot of trouble. Okay? So these numbers are very easy to play with. This is sort of like what you would call the general prior estimate, or the M estimate, because you call that number M. But this is a couple numbers that are really worth putting in there and really playing with when you're applying rule induction to some problem. Okay? And this is much easier than dealing with chi-square and all of that stuff that we're forcing you to do in decision tree induction. We just picked the most painful method because we want you to suffer. And as I mentioned, this is not just a problem in rule induction. What you just learned in the last 5 minutes is something you can apply anywhere that you're doing probability estimates. In natural language and speech, for example, people estimate, all these, probabilities. Like, the famous Google machine translation model is just a bunch of n-grams, right? N-grams is, like sequences of n words and how often they occur. The biggest problem when learning large n-gram models is exactly this problem. I make the n-grams longer, and then the probability estimates start to get very unreliable, so the smoothing becomes really, really important. By the way, this is often called smoothing. Because obviously what it does is it makes my probability estimates smoother. They don't jump all over the place anymore. They're very smoothly from your prior to the truth. Okay. Questions? All right.